evening, and welcome to tonight's webinar on visualizing calculus with Classpad.net. My name is Amy Chow, and I will be one of the moderators tonight. For the sake of webinar quality, we will keep everyone muted and all videos turned off except for the presenter. If you do have a question, please type it in the chat panel, and either I or Karen Greenhouse, our other moderator, will respond back or ask the presenter to respond to the group.
Oops.
Like I mentioned, my name is Amy Chow. I'm the National Training and Product Manager for Casio's Education Division. We also have Dr. Karen Greenhouse with us tonight helping moderate, and our speaker tonight is Ish Zamora, who is the Math and Science Department Chair at Bloom High School in the Chicago Heights area in Illinois. And I'm going to go ahead and pass it over to Ish now.
Oh, I've got to add something to that promo, that information. I'm also in charge of PE.
Oh, that's right. I forgot to add that part.
No,
that's the most interesting thing.
Yes.
Yeah. Hey, welcome to your job. You're also in charge of physical education. Woo!
Now, Ish, you should be able to just start sharing.
All right, so let me share my screen. Oh, let's see. Multiple sharing options. Oh, let's see. All participants. Uh-oh. Continue. All right, there we go.
All right, perfect.
There we are.
Nice.
All right. So welcome aboard, everybody. We're going to be talking about calculus. If you haven't used Classpad.net, it is totally free until December 31st. After that, just about everything on it is free. This is what it looks like when you launch. You can click Start Exploring. There is a slight difference between the Start Exploring page and the page when you sign up. If you sign up with your Google account, you can have unlimited storage. You can have some calculus of things we're going to be doing. A lot of the stuff we'll be talking about is native, so you don't have to have an account, but it does make it nice and easy if you've got the extra storage and the fact that calculus will be turned on. One way to tell that you are in and able to store is if you have a stack of papers, which I'll go to in a minute, and you also have the little cloud in the corner that lets you know you are saving everything you do. If you're familiar with things like Google, you can give things a title or add a new page. So I signed into my account. So let's launch today's Visualizing Calculus. Here is my folder set up. In here, I've got a Visualizing Calculus folder. What I love about calculus, besides the fact that it's awesome and it's one of those great courses that is just really interesting, and all the math that you started to learn finally has some great applications and great problem sets. So, start saying that, one of my favorite quotes about calculus came from Stand and Deliver, because in there Jaime Escalante says, "Calculus was not made to be easy, it already is." What's interesting about calculus, it was developed to help graph, find planet orbits, look at change and accumulation of change. And one of the features that it has is it lets you graph something without having to plot a whole lot of points. You can tell about curvature, you can tell about maxes and mins, points of inflection, you name it. Calculus will tell you. We start most students, or just about every student in algebra, with looking at points, plotting points, and then finding the slope between the points and finding the equation between them. So I'm just going to show you how I walk students through the development of the difference quotient, which always sounds so much more daunting than it really is. So I'm going to type it up here in my sticky, and it's showing me that I misspelled. All right, so I misspelled a couple. So I can change this. I can fix my spelling or not. Anyway, so I'm going to do difference quotient. My spelling is awful today. But before I do that, I'm going to look at it and ask students, what are you noticing? What are you wondering? What can we do with these two dots? And the only thing that you're seeing is what students are seeing. So they also see a couple of sliders, one for A and one for H. Well, let's press play because curiosity always gets the better of students. And we're noticing that the black dot is chasing down the red dot, but the red dot seems to be moving away. So we could sit there and watch that for a little while, or we could slide it and see, will the two dots ever catch each other? And it looks like the red dot is running away pretty quickly at some point from the black dot. All right, so we got an idea of these two dots are chasing each other along some path. I'm not sure what the path is, but we'll figure that out in a second. Second is, what's H doing? So I'm going to move H a little bit. And it looks like H is moving them closer together. Down to
I think we lost Ish.
I was thinking the same thing.
So Cal, just look at the dots that are still moving.
There he is.
Oh, there they are.
Hey,
Oh, did I blank out?
You disappeared.
you
Yeah.
did.
Oh, I'm so sorry. I was sitting there yammering. That's weird. Well, let me catch you up on what I said to myself. What I'm doing right now is I'm moving points A, and these two are chasing each other along some predetermined path, but it doesn't look like the black dot's ever going to catch that little red dot. And it looks like the red dot is really running away from it after it goes over a hump there. Second one is I got a slider here for H, and H is going to move the objects either closer or further away. So I could move H all the way down to 0, and the two dots would be right on top of each other. What I ask my students to do is, okay, what can you tell me about those two dots? They'll start to say, well, one's further up than the other. Oh no, did I blank out again? Oh no.
No, you're good. You're good.
Oh, whew.
Sorry. I was on mute.
Getting nervous. All right, so one of the things I'm looking at is I'm looking at adding something to this. So I'm going to connect some dots. First thing I'm going to do is I'm going to show the rise and the run, because that's something we find kind of important. So there's rise and run, rise over run. That's the slope. So we know that these two have a rise and run. Now, thinking calculus-wise, I can calculate the slope of the 2 points by just saying, well, that's a difference in y. So I'm going to put this in parentheses. The y-coordinate of the black point minus the y-coordinate of the red point. And I'm using my keyboard shortcuts here. I use the sub score, which is shift underscore. And I'll do the same thing with the x-coordinates, x sub black spot minus x sub red. So that is our familiar equation for the slope, change in y over change in x. We want our students to get a little bit more sophisticated. We also want them to say, you know what, there's a line that connects these two. So I'm going to connect the two with a line. And then when I look at my animation, things should change and adjust accordingly. It may take a second or two to refresh, but that's okay. That's internet connection there. Which my internet connection today is awfully slow. But as we get more and more complicated, we want students to start using notation that we're familiar with. We're familiar with function notation. So I want my students to really think about y sub black and y sub red with a change in h. I can do that in the x coordinate pretty easily. So if I said the red dot is nothing more than the black dot moved over by some fixed amount, which I call h. And I will add parentheses around that. And you notice the software takes care of where it thinks the parentheses are going to be, and then we can adjust it. So it's giving me an answer because it knows H is a quantity that I want to be able to use. So I'll just change this to capital H. So now I'm looking at this as the change in Y over H, which if we did some algebra, we'll notice the X's actually drop out. So I want to be able to find that equation for the Y coordinates. I have to use function notation. Function notation is one of those things that we don't do a lot of early on in algebra, and I think it's a disservice. I think it's a disservice because we want students to be able to plug into equations. We want students to be able to substitute for different values. And function notation actually allows us to do both. And it does order of operations, and you can plug in. You can do all the things you want students to be able to do in a pre-algebra setting, usually pretty easily using the function notation. So now I've got an answer of -1. So you know what? Let me change my function here to a name I don't already use, because it looks like I'm using the F notation. So here we go. So we have f of x plus h, or g of x plus h, minus g of x, or g of x minus g of x plus h, all over h. That's starting to look like our instantaneous rate of change or our difference quotient. The other things I did on here are I created the line that it's going through by using a function I called g. This fancy looking thing here, we just realized, hey, that's nothing more than my slope formula. When I plug in for an x minus this a value, and I think I've got more to show, because if you use your algebra equation, which is y minus y1 equals m times x minus x1. So those are just our old friends using function notation. So function notation makes things look a little bit more complicated, but always have to connect it back to where the kids are familiar and coming from. So here's my function here, all set up and ready to go. I also have some sliders here, but what's great about calculus is you start asking yourself, well, what's the limit as this h gets closer and closer to 0? What's the slope of that line going to be? I get an error because I can't divide by 0, but if I zoom in close enough on these two dots, I will see that there is some change in y and change in x, or there's a secant line right here. Somewhere in between, there's this perfect tangent line that secant line that I'm currently looking at in green is getting close to. So what I'm going to do is I'm going to find that tangent. And here's the tangent point. I don't like it in orange, so I'm going to change the color. I'll go to black. And now what you're going to notice is that as I get closer, those two lines become really close to each other. And when I drop this somewhere in between, it's going to give me an equation that's almost on top of the green line. So I'm pretty darn close. What's really nice is if I look at my two equations underneath, here's my first equation. Here's my second equation. So the black equation is the one the computer is calculating using the tangent function. The one that I've got highlighted over here, which is my line function, I notice I have the exact same slope, but my y-intercept is slightly off. So again, using the idea of a secant and a movable point where 2 points are getting closer and closer and closer to each other until their difference is 0, is I'm getting to the idea that calculus is based on motion, on change, on quantities becoming smaller and smaller or accumulating. So again, a nice visual that if we spend too much time on the ideas here, you get lost in the notation and you tend to lose students early on because of the notation. The notation just reinforces what you're really thinking about is what happens when you move these 2 points closer and closer to each other until the difference is 0. And again, you can't divide by 0. But way back in the day when they started looking at calculus, they looked at these infinitesimal differences to get this secant line to basically become a tangent. And thanks to the advent of limits, you're able to do that. So, okay, that's how I introduce the idea of limits. And secant going to a tangent on an equation. I don't know if you noticed, but on the bottom part, I also had the equation. And I could change the equation to be anything I wanted to. All right. Next, let's go with the classic bug on a wire problem. This problem, when I was in calculus, really bothered me because all it would give me is the top stuff in the blue sticky up here. And it says a bug begins to crawl up a vertical wire at time equals 0. The velocity, which is v, of the bug at time equals t, is between 0 and 8 seconds. And it is given by the function whose graph is shown below. So, okay, so I have a velocity curve here. And the great thing about calculus, again, is you can see it. I want to be able to see it. I can see this curve and trying to explain to students, imagine the bug is walking, but it's not really walking on this velocity curve. This velocity curve represents the speed at which the bug is moving. That right there, you're going to lose half the kids. They need to see the bug. Plus, how often do you get to work with bugs in calculus? We should do it more often, I think. And it wants to know at what value of t does the bug change direction. Kids will look at this velocity graph, and I don't care how many times you say it, they will say it changes when there's a little change in the curve direction. So when the line goes flat, oh, there's a change there, and then it changes direction here, changes direction down here. They're getting confused with velocity, which is the speed of the bug, and the position of the bug. So we've got to marry the two together. So why not put a bug on a wire? What bug is less harmful than a ladybug? Who doesn't love a ladybug? I think everybody does, unless in Illinois we have these that smell like tomatoes. I don't know if anybody else does. It's really strange.
Hey, Ish,
Yeah.
Could you maybe show, because how you put the bug in there, just because I know some people may not.
Oh, yeah.
You know, because
So
you
want behind the
obviously
scenes.
shrunk the bug and did a lot of little behind the scenes with your bug.
Absolutely. So what I did, I added a sticky. I like using geometry stickies or the graph sticky because there's a little option here that says image. So you can add an image from your computer. I don't think I have the bug on this computer.
But what I'm more interested in is if you know how once you enter the image, you get that right there.
Perfect.
What did you change is what I
All
was
right.
getting at.
All right, so let me show you what I changed. So on the background here, where the kids aren't seeing it, I've got this little bug, and I'll pull it up so you can see there's a little wire that connects these two, which means this image of a bug is connected to this control panel. The control panel lets me control where the bug center is, so it's centered at 3. And that's where I've got a line. This blue line is y equals 3. And that's where the problem was saying it has a line or it's climbing up a wire. I could have made it a red wire. I also have the controls of the y, the position of the bug, which I'm using a function. And I'm using this function down here. This is a piecewise function. It's a little nasty, but the kids don't need to see it right now. I just created it because I needed this velocity function. The velocity function is just a bunch of straight lines, so I created that. The angle of the bug, I could change the bug and say, okay, you know what? I'm going to face the bug 90 degrees, and it'll rotate the bug. So I've got full control of the image of the bug. And then if you are looking at a sci-fi movie on late night TV, you're looking at giant bugs. So you can also,
I mean, the images tend to come in very large, and
yeah,
it's nice to know that you can adjust.
you can manipulate them any way you want. So I want to make the
Exactly.
bug noticeable, but not too intimidating. And then I put this in the back. I could change if it was in the front or the back. I like to keep it in the front just so you can see that it's actually on top of the wire and not under the wire. And I also hide this control panel for the equations. These are piecewise functions. And this first piecewise function I took by looking at this problem and then just finding the equation of those lines. And then the tougher part was trying to figure out the position of those. So that took a little algebra, but that was just me showing off.
So when you say hide, you're just sticking them behind stickies on top. Yeah. Eventually, just so everyone knows, it is coming where you can actually hide stickies. So anything you create that you don't ever want them to see, even if they move a graph, is going to eventually be hidden. I don't know when, but it is coming.
That's awesome. Yeah, so it just took a couple of clicks, so you can't really see it. You can tell there's something back there, but you don't really need to know what it is. So the bug on the wire, now the students, anytime they see a velocity curve, they have a hard time translating that to motion. So let's actually do it so that I can talk about how the motion of the bug is related to its position on the velocity curve, in this case, or velocity set of lines. I'm going to move my slider a little bit. So I'm going to press play, and while it's doing it, it moves at a rate where I can kind of talk about it. So the bug's moving, and it's going a little bit faster every time. So it's moving at an accelerating rate. So you notice it's moving faster every time until it reaches that cusp at t equals 2. At t equals 2, something else is going to happen. What's going to happen is now the velocity or the speed is not going to change. So between 2 and 4, the bug will keep moving, but it's not going to speed up. It was speeding up when I looked at it between 1 and 1.2. It moved a certain amount. Between 1.2 and 1.4 or 1.6, it moved faster and faster until it reached 2. Now, it should be moving, but it's still going at the same pace. It's not going faster between 0.2 and 0.4 or 0.6 or 0.8, but it's still moving. So then I'll pause when I get right at 4 and ask my students, tell me about the motion of the bug now that you have an idea that this is the speed. So the bug is still going to be moving, and this is where students will say, oh, it's going to move backwards. Great opportunity for them to get their notion out there, but it's not necessarily going to match their instinct. So I'll press play, and then half the class will go, ah, but they notice that, okay, it's still moving up the pole, but it's doing it at a decreasing rate. So in other words, it's slowing down. So we should see the bug slowing down between 4 and 6 seconds. So it's getting closer and closer to 0. Once it hits t equals 0, or distance is 0, or acceleration or velocity is 0, it should stop. So at 6, that bug has come to a dead stop. And the first time we do this, we just focus on the bug. And then we'll notice that the curve is underneath. Now is when you start realizing this bug is moving backwards at an accelerate or a decelerating rate. So it's going to start moving backwards, and it's going to start fast, but then it's going to slow down. And then it's going to keep going backwards, and it's going to go backwards at an accelerating rate. So it's a great opportunity to let kids see motion on one side, velocity on the other. When it comes time, we could add an acceleration curve to this so that we could see the change of velocity. And by then they've experienced this idea enough where they'll be able to say the acceleration between 0 and 2 is constant because the slope there is constant. The acceleration on the flat is 0, so the curve is going to be at 0. And then it's going to be some negative number, and then it's going to be another negative number, and then a positive. So they'll be able to piece together an acceleration curve based on the velocity, based on the motion of the bug. And this is a classic old calculus problem. If you Google bug on a wire, you will get this actual problem, which is at what value of t does the bug change direction? Well, what better way to make a bug change direction than actually going to the point where the bug changes direction, which is at between 5 and 6. So 5, 6 stops, and then at 6.2, it starts moving backwards. So that's when we notice the curve is underneath the y-axis. Kids focus so much on the x-axis in calculus. What we really want them to do is focus on this y-axis. And it's hard for students to do that. That's why you need a visual. So something else I was able to do was actually find the question that this is based off of. Like I said, all I did was Google it. There's a ton of places on Google that have it out there. I just took it right from there, copied and pasted, typed the question up, found the equation of these lines, worked backwards to find out what the position curve was, and then during which time intervals is the bug slowing down. So you can tell when's it slowing down, when's it speeding up. But now there's a connection, so you get to visualize the two things happening at the same time. Again, more students love the bug than just about anything else. And my students would always come back and go, can we do another bug problem? What's nice about doing the bug problem is I can do a different curve. So I'm going to turn off this first curve. Because once the students think they have it, that's when you really have to hit them with something else. Hit them with something they haven't seen before. So I will turn on this one. So now we've got a bug that appears to be surfing. And this is called bug2. So I have a function called bug2, and I'll show you how to do functions in a minute. Make sure I got the right function here. Oh, it's capital B. The computer is will do whatever you ask it to do. So if I ask for function bug2 without the capital B, it's looking for one that is exactly called bug2. There isn't a function called bug2, but it would look for it. So you got to be very careful about how you define your variables. So all right, so now I got bug2 here, and I will press play. Oh, and I've got my wrong crosshairs. I'm going to pull up the correct crosshairs here. My crosshairs are bug2. Bug2. I add the crosshairs because they need to be able to see on the velocity curve where this bug is as far as the velocity is, so that when you pause it, it's actually pointing out on both curves. And right now I'm way off of the reservation on that one. Oh, there we go. So again, what are we noticing? We're noticing the bug's going up the wire. It's slowing down till it gets to a 0 where it stops. And then what's it doing? It's going to continue to go down the wire and changes direction. So there's a lot going on here. And again, you can change and add any curve, any function you want. The bug will be linked to it. So there's a link between the two. You're able to now make some conjectures about how the bug is moving to the velocity curve back to its actual position. All right. So those are some of the big heavy hitters in calculus. Now let's get to some fun. And by fun, I mean optimization problems. So let's go with an optimization problem. Let's see, should we go with, I'm going to go with in the gutter. In the gutter is an optimization problem I've used in AP statistics. I've used it in algebra 2. I've hinted around it in geometry, in algebra 1. So there's a lot of applications. Let me set up the gutter problem. So a gutter is being designed to move water away from a roof at So what angle is needed to maximize the amount of water the gutter can move? So we want to try to move as much water out without it spilling over the edge here. So there's the edge. The other end is the cleat here. This is the part that nails into the fascia or into the roof of the house. So you can adjust the angle using this dot here. And you notice the area changes, the angle in here changes. And I'll show you how I added some of those features because we're going to do some calculus since this is a calculus talk. But let me show you how I added some of those. I'm going to add an angle here. All I'm doing is selecting. This is in my geometry sticky, by the way. In my geometry sticky, I click on the arrows, click on the two sides. Up on the side here, I've got my ability to do all sorts of great things like adjust this. I can measure, which is what I want to do. I want to measure that angle. I can do the supplement of the angle. I can do the angle as a rotation or just the regular angle. I'm going to change how that looks. So the properties, I'm going to change that to a blue angle. You could also add tick marks. So if you're doing some geometry where you're looking at congruent angles, you can actually add tick marks to angles and sides, and lots of different tick marks can be added. I'm not going to use any tick marks on this one. I want it to stand out from the reddish angle on the bottom. So that's where I changed it. So what I've done with students in geometry is they just move that angle until they get a number that is the biggest they can possibly be. So they keep an eye on that, on the area, which is right in the middle. And when they think they have a maximum, they'll stop. So it looks like the maximum is, and again, you're eyeballing it. So it's right around there. Angle there is 63. Students in geometry, I would give them parts of this, or I would take parts away and say, okay, you can only measure two things. Measure any two things you want. You have to find the remaining given the information you've got. So they could measure one more thing. So I'm going to measure the top, and that looks like a trapezoid to me. So hopefully they're looking at it and going, that's a trapezoid that has a top of 11.22 and the bottom is 6.77. Now they have to figure out what the height is. So we know from our days in geometry that I could go 11.22 plus top plus the bottom, 6.77 times a half. I forgot my half. Times some height. So I don't know what the height is. But I do know that the area is 40.22. So in geometry, they have to solve this themselves. I'm not going to let them not solve it. Here, we've got the ability to go ahead and solve. And you notice the minute I start typing, I get lots of different options on things I can do. I'm going to solve this equation. I don't even have to tell it for what variable. It knows there's only one variable there. It's always a good idea to tell the calculator, hey, you know what? I want to solve it for H. Gives me an exact answer there. I want the decimal approximation. So it's about 4.47. The great thing is kids will believe anything you say as a teacher. Unless they get the answer wrong, they don't believe anything. They think math is broken. They think you lied to them. They think something is wrong. So the best thing that I have found with this software is you can show you that that answer actually makes sense. So the kids can actually double check. So I want to find the height or the distance between that point in the corner and the bottom of the gutter. And I'm going to go to measure. And I will go length and distance. And it gives me a number. Now, it's not just a magic number. I don't trust it. So what's awesome about this, I didn't realize this until the other day. When I click on that B, it shows me how it calculated that distance. That is perpendicular distance to the base, which has been extended. It includes the dotted line. It includes the right angle. It includes the fact this is a solid line going right down to the bottom. Awesome. I can't stress enough how important this is and how great of a teaching tool it is. Plus, as a student, they get to see, oh, okay, the calculator said I did it right because my answers are right. And it gives me more decimals than the original. I could change that to give me more decimals, but we won't go there. So, okay, that's a geometry approach. This is a calculus talk, so let's use some calculus. I'm going to delete that sticky for now. So in calculus, we're looking at optimization. So what I am really doing is, you saw that triangle that I created earlier. I'm going to pull it back up because it'll take me less time to create the triangle. Here's your triangle. That purple angle is the same as the purple angle along the bottom. So I'm going to do some calculus here. I do know the length of that side, that hypotenuse, because it was there a minute ago. It's about 5, so I'm going to leave it at 4.99. So what I've got is, I've got a right triangle where I know the hypotenuse. So using some calculus, I've got to try to optimize this equation, focusing right now only on trying to find this perfect angle. What size angle should I have? So I'm going to start creating some calculus here. So I know from my days in calculus that the area of that triangle is the base, 1/2, the base times the height. Now, base and height have not been defined here. And I know I've got 2 of those, so I'm going to wrap that up into 2. But I want to maximize the area of the gutter. So the area of the gutter is going to be plus this base 1 plus base 2, which I already know what the measures are, times the height, which again, I know what it is, but let's pretend we didn't. And I also need a 1/2 out here. So now I'm going to replace things I know. I know base 1 is 6.77. Oh, but wait, it's not a trapezoid. That's a rectangle. So I don't need base 2. I know the height is a function of a sine or a cosine. So, okay, now, since purple angle is 67, about which I don't really know what it is for this problem, so I'll delete that for now. But I do know that that height is the side that's opposite over hypotenuse. So that looks like a sine. Opposite over hypotenuse, or hypotenuse times the sine of x. All right, so that's the going to give me the area. The base is going to be the hypotenuse, which is 4.99, times, again, it's going to be the short side. My triangle disappeared here, but it's a short side, and that's going to be the cosine of x, because I've got the adjacent side, which is the short side of the triangle, and that's over the hypotenuse, so y over that. 4.99 cosine times the height, which I already said is 4.99, times the sine of x again. And I'm going to put a multiply in here just to be safe. Let me expand this out. So right now, that's not telling me a whole lot of anything. What I do know is that the maximum or minimum is going to occur when this function goes to 0. So I'm going to give this a name. So I'm going to call it a of x. And I will define that variable. I'll use the colon equals, we'll define that variable, it locks it in. It is a function of x in terms of the angle. So notice the computer has said I'm done. That's good, because what I want to do is take the derivative and solve for when this equals 0. First thing I want to do is take the derivative. So math, derivative in terms of x of a of x There's my derivative in all its grandeur, all its glory. There it is as a decimal. I will leave it as the exact answer. Now I want to solve this equation when the derivative, when this answer equals 0.
That's a scary looking.
Oh, it is, isn't it? What's even scarier is the answer that comes out. The answer is just like, oh my gosh, what is that? Let me go to decimal. I'll go to the decimal approximation. Way too much information. You know, I don't want any angle other than the ones between 0 and 180. So this is limiting the function. So this is only looking at answers that are between 0 and 180. And you know what I did wrong? Let me put in, I'm going to copy this because when I hit answer, it copied the answer from the previous one. And anytime I use the word answer, it's just going to go ahead and plug the answer. Again, looks really scary. It's easy to talk through with kids. They really do get a kick out of it. And they get to see the answer come up. Oh, what happened? There it goes. Let me go to SD. So it's saying it's like 56. So somewhere in here, I am missing a piece of the puzzle. What piece of the puzzle am I missing? Base height.
I can't help you there, Ish.
Oh, Dr. Green. 1/2.
You're hurting my brain.
4.9 sine of x times that, base and height. Somewhere in here, I've got a number that's a little off. Anyway, when I did this earlier, it did come out to be that 63 and some change. Here's what I really love about the problem. There's the calculus version of it. I've got a table of values down here that I could actually do the same thing using some statistics. So I use the stats window down here below. What that's going to do is when I move this angle, one thing that we don't do enough with kids is collect data.
Mm-hmm.
So the great data collection piece, I'm going to use this inside angle, and that says 136.42, and the area there is all right. I'll do a couple of more. I'll do 3. I'll do one that's below. So let's see, that's 39. Oh, that's the area. And then the angle's 110. And one more will go wide. Giving me an area of 14.25. All right. So here we go. So you notice that those points have been plotted. Plotted those 3 points. All I'm using here is a graph sticky with the ability to put in a table and also to put in a plot. So I'm just plotting the points here. So it plots the points. It gives me this sticky. I've asked the computer to take these 2 bits of information and create a regression equation. I went with a quadratic regression. It pulls up a quadratic regression here. And from that quadratic regression, what's really nice is since this is in the computer, when I click on it, it's going to give me some important points like here's the maximum. So now it's giving me a maximum area of 140.15 at an angle of 115. So let's see. I'm going to move this depth out of the way a little bit. I'll move the word angle. So when I come back around and get to 115, I'm looking at this angle alpha. It should be pretty close to the high 115.87. So I think you get the idea. I'm narrowing in on it, and it's right in there. So again, I got pretty close using the stats feature, got me the answer. I used some geometry to get this answer. I used some calculus. I'm missing something on the calculus, but it got me the same answer. So what's really nice is you've got one problem that you can use so many different ways. The calculus is just one way of approaching that problem. All right, so now let's go to the good parts here. My favorite calculus problem of all time. We all have one, believe it or not. Even Dr. Greenhouse has a favorite calculus problem.
I don't remember that I have that.
It's in there somewhere.
Okay.
It's a repressed memory.
I like the bug one. The bug one was good for me.
I think you really like this one. This is the old sliding ladder problem. Oh,
you disappeared.
He is currently working from home, and he's a math ed major. Oh,
you're back.
He's a math ed major at Illinois State University, and he is working from home, and he just did related rates, the sliding ladder problem. And I told him, I bet you probably didn't do it the way I approach it. And he's like, Dad, knowing you, probably not. So I'm glad to know he knows. I like to approach things a little differently. So let me zoom in on what's happening here. Nobody was harmed in the making of this TikTok video. By the way, math people out there, TikTok is a great source for math problems. A lot of them are unintentional, but they are great. So just scroll through all the stuff that you don't want to see, get to the good ones. This person is not using the ladder the proper way, and they are sliding down the wall. The classic calculus problem says you have a person on a ladder and the ladder starts to slide. In the calculus problem, though, the ladder just starts to slide on its own. So what happened here is the ladder slides down on itself, it compresses, and then starts to slide down the wall. So I can measure some things like how far is the ladder from the wall? So let me grab a little arrow. That's that distance there from the wall. Originally, it didn't give me that, but I changed the name. Calculus should make sense, not because it has to, because it just does. So that's the distance from the wall. I know the ladder in the picture is 2 units long, and the ladder I'm estimating to be about 8 feet at the position when it slides down on itself. Great conversation with kids is, kids, tell me how long you think this ladder is. They will give you a number. Use that number. So in this case, it's 2 units, but if they say it's a 10-foot ladder, okay, so it's a 10-foot ladder. 2 feet represents 10 feet in real life, bringing in some conversions. Second thing I've got to find out is how far did this ladder slide from the minute it starts sliding. So all I'm doing is estimating, I'm counting. So when it hits 1, and I put this dot D at 1 second, where I think that ladder is at 1 second. Does it have to be exact? No, we know the person wasn't harmed, but now they're hooked. They know some things about the picture. They know some things about how far things are, how long the ladder is. This in 1 second is how fast that ladder is sliding away from the wall at that moment. The question is always, how fast is the top of the ladder, or how fast is this person falling, or their head falling at the other end? There's your calculus. It's a related rate problem, which kids cannot stand related rates. It is a tough concept when all you've got is a picture with no sliding person. So if I had taken off my moving GIF back here, it's actually a moving PNG file. There's webinars. I think we have videos.
There's a whole webinar on how to
Awesome.
convert and put it in. Yeah.
Yeah, it's such a cool thing to do. There's so many great ways to teach math without actually having just to do words. And this is one of them. So I know from the geometry here that it's a right angled wall. So the distance from the wall, quantity squared, plus the height up the wall squared equals the ladder squared. So we want to find out the rate at which the top of the ladder is falling. So how fast is the top of the ladder sliding down when the ladder is 1 foot from the ground, or in this case, at time after 1 second. So I'm going to change this to say after 1 second. After 1 second. There we go. A lot of these questions, I don't even show the students. They get so interested and curious. After they stop laughing and start focusing on the math, they will start asking questions like, well, how far away is it? How long's the ladder? How far did they slide backwards? How far did the top of it go? I really can't tell because it's blocked by this little bit of wall. Coincidence? I think not. So what I got to do is I got to take the derivative. So the derivative of this function, I'm using a text sticky. Now the text sticky, I'm allowed to write some equations in here. So I'm going to take the derivative in terms of the actual words. So if I take the derivative of from the wall squared, that's going to be 2 from wall times the derivative of from the wall. That's going to be d from the wall over dt. Because we're doing this in terms of time. Plus the height, the derivative of the height is 2 times the height times the rate of change of height. And that's dh over dt. Equals, do the same thing on the ladder, 2 ladder times the rate of change of the ladder. Well, we know some things. We know the distance from the wall. The distance from the wall is 1.10, but if we keep in mind the ladder's 8 feet tall, you're multiplying by 4. So from the wall is 4 times 1.10. And then I'm going to multiply that by 2 because there's also a 2 in there. And now right now, this is just text. I'm going to do the actual calculation on the side. I want the students to think about all of these pieces one chunk at a time. So after 1 second, it goes 1.05 times 4, because we have to multiply by 4, and that's the rate of change. 2 times the height of the ladder that goes up, which I don't know, but I could use some Pythagorean theorem. So let's use some Pythagorean theorem here. So I got 4.4 squared. That is the along the wall, or along the floor, plus x squared equals the ladder squared, which is 8 squared. And again, remember, I'm multiplying everything by 2 to get these distances. And I want to say solve. I keep forgetting to add that. And it'll solve for x. So I don't want the negative, I want the positive. So that's 6.6. I'm going to go 6.7. dh dt, I don't know that, which is a good thing because that's what we're trying to find out, is how fast is this sliding down. Now, here's the part that throws my kids. My students are always wanting to put in there 2 times 8 times the rate of change of the ladder. How fast is the ladder changing? The ladder's not changing. The ladder is fixed. So the rate of change of the ladder is actually 0. That's the part most of my students will go south on. That's where they don't quite get it right. So that is the equation that I want to duplicate down here and solve for when that equals 0. When that equals 0, I don't think I can copy and paste it, but I'll try it anyway.
Well, you can try. I just don't know if the time symbol will translate.
Right. Yeah, it won't let me. That's all right. So let me type this in. Again, I want my students to be able to show me all the work so that the sticky that they turn in, when they turn in this assignment, there's a way to do this, by the way.
But you know what you could have done, Ish, and I'm looking at time, just giving you a warning here, but what you could have done instead of typing it as text, actually typed it, like go into the math type.
Type it in the math.
And type it in as an actual, using the template, and then you could have copied and pasted.
Right.
Because then it would have been interpreted as a math problem versus
Oh, awesome. That would have. Anyway, you get the idea. That's the calculus part. You solve it, you plug it back in, figure out what it is. Oh, by the way, here's the OSHA. This is the OSHA regulations. This is X along the top, X over 4 along the bottom. So the question is, did this ladder meet OSHA regulations? This person should have checked their OSHA
regulations
rules and known that is not OSHA appropriate. All right, last one. I will do this one fairly quickly. Super fast.
Super fast.
Here's the power of Classpad. Accumulated area. This is accumulated area under a curve using Classpad and a slider or 2. All I'm doing is moving A. And the other thing is, how many slices do I want to make? So I'm going to make like that many slices, and I'm going to zoom out. I've got some different functions in here that you're looking at a Riemann sum, where you're looking at a lot of different sliced rectangles to approximate the area under that curve. Once you take the sum of that Riemann, you can actually find the integral between points A and B, which in my case are -1 and 3. And then you get the actual calculus, which is what's the actual area, 56 over 3, of that function between those 2 points. I am approximating them using a Riemann sum, and the Riemann sum is really not that tough to do. The hard part was trying to figure out what this integral, or the integer of a times x over a, to make my little steps. Thank you to Nathan over at Casio.
Yeah.
Nathan is amazing.
I think can't you, in that integral area, instead of lower upper being constants, couldn't you just put in A and B? I think you can.
I think you can.
Because then you'd be able to move that and match not only the rectangles, but also the area.
Yeah, look at that. Gives me the same thing. And then
so
when
then
I move
if you move the sliders now, it all goes together.
Yeah. Oops. Yep, there it is. 94 over 3. And it gives me the area. And it took a little doing, but trying to figure out how to shade the rectangles different colors, it was kind of fun. So notice the functions here. The functions here are really complicated looking, but they're really simple. So you can do some Boolean logic in there to make it work out.
Can you share any of those with people if they want?
Oh,
instead
absolutely.
of recreating, just thinking.
Yeah, I will share all of the things that are inside this calculus folder. So there is 5 of them here. I will share all of those. I will make those public tonight. And anybody who wants to be able to,
basically the simplest way is just send me the links. And so when I send the follow-up email, everyone will get it.
Perfect. I will do that.
Awesome.
And I will stop sharing.
Okay. Well, thank you so much, Ish. I always learn a lot because I have forgotten pretty much all of my calculus. So though that last one with the ladder, I have done that many times in geometry. So it's all good. Can you see my screen now?
Absolutely.
Okay, so real quick, thank you again, Ish. That was great. And Ish
Sure.
is going to be doing another session, but this time with our graphing calculators, right? Or is it scientific?
It's going to be a little bit of both, mostly graphing, but I will pull in scientific to pull up some QR codes.
Okay. Oh, the 991. Love that.
Yeah.
So that's November 19th, same time, 6:30. That's going to be our last webinar for the year. We're going to take a break for the holidays, and we'll be back in January with our equity webinars and some more Classpad and calculators. Don't forget to visit. We have all of these recorded. If you want to sign up for this last one, it's going to be right there. And visit us on social media. Tell us what you'd like to see. We're in the midst of planning for our webinars next year, so we would love some topic ideas. And we hope to see you again. And thank you for joining us this evening. And thank you, Ish.
Thank you, everybody. See ya.
Have a great night, everyone.